All right, good morning, everyone. So we're going to get into how we do the training of the Gaussian mixture model today. So let's just kind of review the overall procedure, how we use this for clustering. So our Gaussian mixture model looks something like this. We have K, capital K, different Gaussians. Each one of them has a mean and a covariance. Covariance you can tell by how these contours are stretched. And in addition, it could be that one of these has a lot more samples or a lot higher probability than the other. Overall, the model looks like this. We say that X is coming from this distribution. That's a sum of scaled Gaussians, each with a mean mu k, covariance qk, with these weights that are non-negative and that they sum to 1. And yeah, so importantly, we said that we can think of this as a hierarchy where there's a hidden random variable, which we call kappa, which is a variable that tells you which of these capital K clusters the point lies in. And then, so then you can say that given that you're in cluster little k, this would just be Gaussian with mean mu k, covariance qk. So it's a nice way to think of this as a two-stage process. First, there's a random variable that tells you which of the clusters you're in. Second, given that you're in a certain cluster, you have just a Gaussian with a mean and covariance. Okay, and we're going to call that kappa, is that hidden variable. And we worked out some, so from that viewpoint, these weights, gamma k, these are just the probabilities that kappa equals k. And then these Gaussians are the conditional probabilities of X given that kappa equals k. Okay, so and then based on this, we said that we can view clustering as essentially computing the probability. If you give me a test point X, then I want to compute the probability that kappa equals K for each of the different possible Ks given X. So these are these conditional probabilities that tell us the clustering of that X. And we used Bayes' rule to reorder the conditioning here into something we're familiar with here, times another thing that we're familiar with, and finally divided by a normalization constant, which is really this whole thing. So that gives us a way of writing this probability that X belongs to cluster little k as this, which is written in terms of all the things we know, the weights, means, covariances. So if I can compute these probabilities for all the different values of k from 1 to capital K, then I can just find the most probable of those, and that is going to be my clustering of that point X. So that's the idea behind how we can use this Gaussian mixture model for clustering. Any questions on this? Is this making sense? Okay, so here's the summary. So we actually, given this data set of all these X's, we want to cluster every single element in our data set. So the first step, which we haven't described yet, but will be the main subject of today's lecture, is how to find all these Gaussian mixture model parameters from our data. So assuming that we've done that, our next task is to compute the probability that kappa I equals k for all the different k's, 1 through k, and also do this for all the different I. So essentially, we just plug into all the different K's and all the different I's, and we can come up with a big matrix of probabilities. And then for each I, we search over the different K's to find which is the most probable kappa, the most probable cluster assignment for every I. And that gives us the clustering in the end that we want. So moving on to what we're going to talk about today, we need to fit these parameters. How are we going to do this? So like we've used many times in this course, we'd like to use the maximum likelihood framework. So we want to maximize over theta, the probability of x given theta. Or similarly, we could maximize the log probability of x given theta, the log likelihood. And if we plug in our expression for that likelihood, it looks like this. And then the sum comes out here. So the trouble is that this is a difficult optimization. Anytime you have a log of a sum, that's a challenging thing to deal with. So this is a non-convex problem, and we are going to come up with an approximate solution to this maximum likelihood problem using something called the EM algorithm. So that's what I'm going to describe today. Okay, so the EM algorithm is a generic algorithm that can be applied to ML estimation and other things. We're going to use it. We're first going to develop it more generally, and then we're going to apply it to our Gaussian mixture model. But it's a super useful algorithm you can use for many, many other problems beyond this. So again, the goal is you want to do ML estimation, but often the likelihood is not simple. You can't solve it in closed form. It's non-convex. What do? So EM algorithm gives you a solution to this. So this algorithm is guaranteed to converge to a local maximum of the likelihood function. It's an iterative algorithm, converges to a local maximum, but maybe not the global maximum. So you have to be a bit careful. You need a good initialization to avoid bad local maxima. So this is the case in general whenever you do non-convex optimization. You have to worry about bad local maxima. You have to have a good initialization to avoid them. Okay, so the way that the EM algorithm works is, first of all, you identify some hidden variables. We're going to call them Z. Then you alternate between estimating Z and maximizing theta. So you keep getting a better estimate of Z, better ML estimate of theta, back and forth, and hopefully, so eventually you will converge to some local maximum of the likelihood. Hopefully it's a good one. So there are two steps in the EM algorithm, the E step and the M step. It stands for expectation and maximization. So it's a little bit, there's a lot going on here when you look at these expressions, so let me try to break it down. So over here, we have the log, not of the likelihood, but of this joint probability of X and Z. And this probability is also a function of these parameters theta, which here, these are tunable parameters. So this is just an expression that we have to know, what this expression is, mathematical expression. Then we're going to plug in to this expression these random variables, and now we're going to take an expectation over them. But let's look closely at the form of the expectation. It's the expectation of Z conditioned on X and parameterized by our current guess of the thetas. Okay, so one thing to make a distinction about is the difference between this theta and this theta t. So this theta over here is like a free variable that we want to optimize over, whereas this theta t is our previous optimization that we completed. Okay, so theta t is a constant. This is like a variable. Once you do this whole step, you're going to get a function of your new free variable, and it's going to depend on your old theta t. Then, in the m step, you simply maximize this over your free variable, and that gives you your next guess. And then you repeat. Now you have a better guess of theta t, or of theta called theta t plus 1. You come back to this step. You once again repeat the expectation of this, but now you're using your new thetas. You get a new q, you repeat. So you keep getting a better estimate of theta each time. So, okay, any questions on that? Actually, let's do one more thing. Let's take a look specifically at the form of this expectation, just because there's a lot going on. So when you have an expectation, in this case, this is expectation of z given x and parameterized by theta t. That means you have an integral of this quantity here times the distribution that comes from this expectation, right? That's always how we define expectation, is we have a density and then the thing we're taking the expectation over. So here our density is pz given x parameterized by our old thetas, because that's how this expectation is defined. All right, so we are going to we're going to integrate out the z's. This will remain a function of our data x, but our data x is just a fixed thing. We've collected this data, we're plugging that in. The z's are hidden variables. We do not know what the hidden variable is exactly. So we talk about this as estimating z, because we're going to compute this posterior distribution. In a sense, this tells us everything that we could ever want to know about z, given our data and given our previous guess of our parameters. So from this distribution, for example, is what we would call a posterior distribution. If you looked at the mean of this, that would be the minimum mean squared error estimate of z. You could look at the mode of this to get a different estimate. There's all sorts of estimates of z that you can create from this distribution. In a really simple case, maybe this distribution would have all of its energy concentrated at one value. So this is this Dirac delta. It's like a spike where z equals z hat t. So this is just a simple case to try to understand what's going on. This would say that once you compute this, you're absolutely confident that z is z hat t. If that's the case, then when you plug that into this integral, essentially what would happen is, because of what we call the sifting property, when this delta is in the integral, you essentially just replace this with z hat t. Okay, so what I'm trying to say here is that in the simple case that you're absolutely confident that your hidden variables equal z hat t, then what happens when you compute this whole thing here is that you simply take your log of your joint probability and you just simply replace this z thing with z hat t. That would be like the simplest case. In reality, it's more complicated, because when you compute this, it tells you you're not exactly sure what z is. Z has a range of possible values that explained by this density. And so really what you're doing is you're averaging this quantity over all the probable values of z, not just this single value z hat in practice. Okay, so this is sort of just a way of trying to interpret this. So this guy here, this q, is like an average of this over all the z's that are probable given your data x and your previous guess. Okay, so this is the EM algorithm. Now, where this comes from, there's sort of a nice explanation for this based on something called minimization maximization, which I'll describe next. But before I move on, are there any questions about how anything is set up here? Yeah.
I understand the Sifting property, but I don't understand why it's being brought up. Like, how does it apply?
It's just my attempt to make sense of what this is. So like how you can interpret this. So essentially when you do this expectation of this quantity, you are taking this quantity and you're averaging it over all the probable values of z of your hidden variable. You don't know the hidden variable, so you can try to estimate that hidden variable given your data and your previous guess of the parameters. And that's going to give you like a range of different z's. Some are more probable, some are less probable. And then what you're doing is you're essentially averaging this over that distribution of z's. So in the simplest case of that, the simplest case would be where this density puts all its weight on exactly one value of z called z hat t. And in that case, all you're doing is replacing this with z hat t. So that's what I'm describing this. This is just like a really simple case for understanding. But it doesn't, in practice, this will not happen, so this is not super important. It's just my attempt to try to explain what this means here. Does that help? Okay. All right, so so this might seem like weird, like where is this coming from? Why are we doing this? So, so the best explanation is that this is an iterative maximization of a lower bound. So first let's talk about why that is, and then let's talk about an example of why you would want to do this. So we can start with our log likelihood. This is just a plain old log likelihood. And we can write it like this. Now this might be a weird way of writing it because, so notice we have an integral over z. This quantity, likelihood, has nothing to do with z. So you can actually pull this out if you want. And when you look at what remains in the integral, once that's gone, you're just integrating a density p hat over z, which you know integrates to 1, right? So hopefully it's clear that these things are equal no matter what p hat is. Does that make sense? You're just essentially rewriting this in a complicated way using the fact that for any density p hat, that density integrates to 1. Okay, of course, there's a reason why we're doing this. But does everyone understand why we can write it this way? Okay, so now let's expand this p of x parameterized by theta in another sort of weird and complicated way. So let's write it like this. So clearly you can see the p hats cancel. And now the last step, which might not be super obvious if you're not used to thinking about conditional probabilities, is that the joint probability of p of z and x divided by this conditional probability z given x is just px. Okay, so what we're saying is p zx over p z given x equals px. Okay, but that if you just write it this way, then hopefully that looks familiar. That's just the usual definition of conditional probability. Okay, so again, it's like it might seem weird that we keep writing this likelihood in a more and more complicated way, but we're about to finish and show you why we're doing this. So the last step is to realize if you have the log of a product, that's the sum of the logs, right? So I can expand this into, actually, we can go even further. I can expand this into log of the joint minus log of this PZ plus log of this ratio. And that's what we've done here. So we have log of the joint minus log of P hat Z plus log of that ratio. When we do this, it turns out that there's a lot of meaning to these three terms. So let's look at this middle one. So if you have any distribution P hat and you have this quantity negative integral of P hat log P hat, that is the entropy associated with that distribution. So the entropy is something that comes from information theory. It basically tells you how much randomness is in that distribution P hat. It's just one way of defining randomness. There's another term that comes from information here called the callback-Leibler divergence. And this is a way to compare two different densities. In particular here, it's being used to compare P hat to PZ given X. And the property of this KL divergence is that whenever the two densities are equal, the KL divergence is exactly 0. And the more different those densities are, the larger the KL divergence becomes. And you can see that if both of these densities are exactly equal, then this ratio is 1 at all z, right? And then log of 1 we know is 0. And then when there's a 0 in here, the whole integral goes to 0. So that's just confirmation of the fact that when these two densities are exactly equal, the KL divergence is 0. But anytime they are not equal, then the KL divergence can grow larger than 0. Okay. And then this last term here, this is this quantity averaged over z according to the distribution P hat. So we can write this as, you take this quantity and you take the expectation, here I'm writing it like expectation over P hat. So we could also write this as expectation over z if you want. But this is sort of where this term over here comes from, this joint. So we'll see that in just a second. Okay, so again, all we've done is we've taken our likelihood and we've written it, or log likelihood, and we've written it in a somewhat complicated way. But the very last step is to exploit the fact that this divergence is always non-negative. So there's a big typo on this page, which I corrected in the notes, but didn't upload it here. So we have to reverse the sign on this, the direction of the inequality. So it should go that way. Okay, so the idea is that if the log likelihood is this plus some positive thing, then when I get rid of this positive thing, this is less than or equal to the log likelihood. So this is a lower bound on the log likelihood. And now we're finally ready to talk about, okay, why are we doing this lower bounding? You can essentially think of the EM algorithm as iterating two steps. First, it comes up with, we're going to give this a name. We're going to call this script L. This is the lower bound on the log likelihood. So first, you choose P hat, because remember, P hat can be anything. Nowhere in here did we say anything about P hat. It's any density. So you tighten the lower bound through a choice of P hat, and then you maximize this lower bound on the likelihood through a choice of theta. So let me illustrate this using this picture here. So imagine that this is your likelihood. Sorry, log likelihood. This is just kind of a pictorial illustration. And if our goal is to maximize this, and then this is theta, is here. So we want to find the theta that maximizes this, which is clearly this theta. But we're going to do this with bound optimization. So this quadratic is clearly a lower bound on the likelihood, right? It is always lower or equal to the likelihood, and in fact, it's at exactly 1 point, it equals the likelihood. So what you call this, you would say that the likelihood majorizes this shape here. It is greater or equal to everywhere, but at 1 point it is exactly equal to it. So we have this lower bound, and let's say what we do is we want to maximize the lower bound by choosing theta. So if I want to maximize this lower bound, I would just take that as the peak of the quadratic. That would be my next theta is here. Okay. Now I want to tighten this lower bound so that it hits right there. So I'm going to come up with a new quadratic like this. And now I'm going to optimize that lower bound, and that would be finding this theta. And now I'm going to majorize things there. I'm going to find another lower bound that hits right there. And I'm going to optimize that. And as you can see, I'm going to get closer and closer to finding the peak of the likelihood. So we're alternating these two steps. We're tightening the lower bound by choosing p hat, and we're maximizing the lower bound by choosing theta. In terms of tightening the lower bound, essentially what you're trying to do is you're trying to make this term as close to 0 as possible. Because when this term is exactly 0, then this, which is your lower bound, equals your likelihood, and that's the perfect lower bound. It's the same thing. So you choose p hat to minimize this, and then you choose theta to maximize this here. You keep alternating. So that's the approach. This is called majorization and minimization. It's a broader topic than EM, but EM is one example of majorization minimization. It does this. There's other approaches to majorization minimization also, but EM is one of the most famous ones. Okay, so now that we have this idea of tightening the lower bound through choosing p hat and maximizing through choosing theta, we can see exactly how this works with EM. So in EM, we have this we just derived on the previous page. This is our lower bound. This is the term that is preventing it from being perfectly tight. So the tightest bound occurs when the KL divergence is exactly 0. And you can see in order to make the KL divergence 0, you just have to make those two densities equal. In other words, all you have to do is set p hat equal to this posterior. And this is exactly what EM does at iteration t. And then the next thing is you just do your maximization. So you have your lower bound, and you just maximize that over theta. So the lower bound looks like this. The second term has nothing to do with theta, so maximizing is really just maximizing this over theta. Okay, and that's exactly these two steps we saw first. So this is the quantity that we just said we're going to maximize over theta, this one. And in the first step, we are going to, when we take this expectation, we're going to choose the p hat used for that expectation as this. So that is exactly why over here, we're taking the expectation of z, condition on x, given theta t. That is the bound tightening density. There are other versions of EM where you say, I'm not going to use exactly this. I'm going to use something that's a little weaker because maybe it's more tractable. And there's also versions where you don't exactly maximize it here. You say, maybe you have a complicated joint maximization that you can't do. So what you do is you optimize it one variable at a time. You optimize the first variable, leaving the rest fixed. Then you optimize the second variable, leaving the rest fixed. And so you're not going to come up with the exact joint maximization, but it doesn't matter because you're still doing this bound optimization. It's just like maybe instead of going to the best theta, you're going to some not quite as good theta, and now you're going to majorize there instead of there. You'll still eventually get to the peak. It's just you'll go there a little slower, but it will be tractable. Okay. So this is the EM algorithm. Like I said, it's super important and powerful algorithm that you can use for many, many things. We are going to now apply it to Gaussian mixture model fitting. That's what we are developing it for. Before I go on to that, are there any questions on anything regarding EM? I know there's a lot of math here. It's the sort of thing maybe you have to stare at it a little bit on your own time, but okay. So in our Gaussian mixture model fitting, we have identified some nice hidden variables. So the hidden variable we're going to use is kappa I. So for every sample in our data set, we want to know which cluster that belongs to. So the kappa I is an integer from 1 to k. And so basically in our EM notation, this variable z that we've been talking about is just going to be a vector of all our different kappas for all our different data points, kappa 1 through kappa n. Okay, so coming back to how we define the EM algorithm, at iteration t, the E step does this. So this is this expectation of x comma z, or now I'm writing z as kappa vector. And it's a conditional expectation where it's the expectation over z given x in our previous theta t. So here again, I'm just rewriting z as kappa because it makes a little bit more sense now. Okay, so that's what we need to do. We need to compute this. So let's see how we can do this. So the first thing is we have this density of all our n vectors xi and all our n kappas ki. But as always, we assume that the different samples in our data set are statistically independent. So this density factors into a product over all our samples of this joint one here, which is the probability of the feature vector xi and the scalar kappa I, and of course this free variable theta. Okay, so as we know, when you take the log of the product, you get the sum of the logs. So let's see what that's going to give us. The sum, we can bring it all the way outside the integral. And then we're going to have probability of kappa given x theta t. And we're going to have here log of the probability of xi kappa I. Sorry, I'm running a little bit out of space. And we're going to be still doing an integral over all the kappas. But we can simplify things a lot here because when you look at this integral over all the kappas, only one of those kappas is involved here. So if I think about all the kappa j not equal to I, basically this term doesn't exist for them. And all you have is the rest. And because this is a valid density over those kappas, when you do this integral, you integrate out all the kappas except for kappa I. That's the only one left. So finally from that, so this integral is, over all your kappas. This integral is only on kappa I. So you integrate out all the kappas except for kappa I. And that's where you get this. Does that make sense? Okay, so now we have a much more simpler situation where I have a single kappa, I have a single dimensional integral. And in fact, remember that kappa is one of a discrete set. So we really shouldn't be writing this as an integral. We should be writing this as a sum because there's only finite possibilities for kappa I. So let's replace that integral with a sum. In this case, this would be like for k equals 1 to capital K. And we'll rewrite this density as the probability that kappa I equals K. And similarly here, we'll write this as the event kappa I equals K. And let's give this a name. So what this is the probability that K is the best cluster for xi based on the parameters that I know about at iteration t. So we're going to call this quantity here. So these are like the cluster probabilities for cluster K, sample I, iteration t. And this joint probability, this is the joint of x and kappa. We can factor this into x given kappa, which we know is Gaussian, right? And then this guy, this is just our weight, gamma k. Okay, so, and in fact, here's the full expression. So this is the Gaussian with mean mu k and covariance qk, and then this is just the weight here. And finally, okay, how do we compute this thing? Well, we actually saw this before, a few pages back. This is this ratio like this. Essentially, we used Bayes' rule to reverse the ordering of the conditioning, and we got this. So these are the gamma k's from the previous iteration. So the difference between this and this is that these are fixed numbers, whereas this is a free variable that we are going to try to design. So these fixed numbers we calculated on the previous iteration. We also calculated our means and covariances on the previous iteration. So we plug all that stuff in, and we get these cluster assignments on this iteration for all the i's and all the possibilities k. Okay, so that's the work in computing this Q function. You can now see that the choice of hidden variable is important, because if you choose a hidden variable where things are intractable, you cannot solve this integral, you get stuck. So when you do EM, there's a lot of freedom in terms of how you identify hidden variables that will affect the derivations, they will affect how well the algorithm works. So it's part of doing a good EM implementation is identifying good hidden variables. In this problem, these are pretty natural. Okay, so that was the E step. The M step goes like this. So we have now computed this function, and now we need to maximize it over theta. Okay, what is theta? Remember, what are our parameters theta? We want to maximize it over the weights, the gammas, the means, and the covariances. So we have to figure out how to do that. Okay, so let's, so rewriting this, here is our sum. This is our sum over I and k of these gammas, and then log. So we're going to do log of the first plus log of the second. So log of the first is log of gamma k, or actually that's log of the second, and then log of the first is log of the Gaussian. Okay, so that's just how we go from here. Rewrite it in a little bit of more convenient form. Now, one thing to remember is that there were some constraints on the gammas. The gammas, they form a PEMF, so they have to sum to 1. They also have to be non-negative, but it turns out that if all I do is enforce the sum to 1 constraint, they will automatically be non-negative, so I'm not going to explicitly force that. But to force the sum to 1 constraint, we have to use our technique from constrained optimization, where we have the Lagrangian. If you remember, we talked about this back in Unit 6. So again, our task right now is optimizing lambda k. Gamma k. There is no gamma k over here, so forget about this. So we just need to maximize this over gamma k. But the gamma k's need to sum to 1. So to enforce that, we add a new variable, lambda, the Lagrange multiplier, and we multiply that by, we rearrange this constraint until something equals 0. We want that this equals 0. And this is our new cost function, and we would like to set the derivative of this to 0 with respect to both gamma k as well as lambda. So first, we're going to see how do I set the derivative to 0 with respect to gamma k. So I compute the derivative of this. It's pretty easy because the only place, actually there's 2 places gamma k shows up, here and here. So here, because of the log, we know this is 1 over gamma k. Here I'm writing the sum over all the different k primes, but there's only one of those that we care about, which is k. So we'll have the sum over I, but not over k prime. We'll have this, but only with k where k prime was. And then this turns into 1 over gamma k. And then over here, this term goes away when I take this derivative. One of the terms in the sum stays alive. It's just gamma k. And, and when I take the derivative of the gamma k, it just turns into a 1. So finally, we just get this. Okay, so we know that this term must equal 0. So let's rearrange things a little bit. 0 equals this. And this is true for all k between 1 and capital K. So if that's true for all k, then I can actually sum this over k, and it's still going to be equal to 0, right? So I'm going to sum this over k. That's going to put in a sum here and here, still equal to 0. But in doing so, I can leverage the fact that this sum equals 1 by construction. So this whole thing just turns into 1. Simplifying the expression. Also, remember that for every fixed I and t, this sequence over k is also a PMF. So if I sum that over k, that also equals 1. So that massively simplifies things. So now we know 0 equals a sum over I times 1 minus lambda times 1. And this sum over I, this is going from I equals 1 to n. So this just turns into the constant n. And now I know that 0 is n minus lambda, or in other words, lambda is n. So we have solved for lambda. Now that we know lambda, we can plug lambda back into here and solve for gamma k. Okay, so the very first thing before we even do that, let's just rewrite this by moving this to the other side and dividing by lambda. We have isolated gamma k. We know that gamma k equals this, but we also know that lambda is n, so we plug n in for this, and now we have an expression of things that we know. So we have solved for gamma k. It's just, we look at our membership probabilities from the previous iteration, and we average over all the samples I, those probabilities, and this is just the average value of that. So this is our new optimized gamma k, so we're going to call that gamma k superscript t plus 1. So we have done our optimization for the lambda k's. Any questions there? That's the first stage, first part of the M step. The next thing is we have to optimize over mu's. Okay, so we go back to our cost here. We set the gradient of this with respect to mu, we set that to 0. The first term doesn't matter, so we can focus on this. So here's that second term. We take the gradient of mu, set that to 0. So because the gradient is linear, we can move this outside. So we need to take the gradient of mu of this log Gaussian. But we also know that the Gaussian can be written as this exponentiated quadratic form. It's exponentiated this divided by a scaling constant, but that scaling constant does not depend on the means. So when we do this gradient, we don't have to worry about it. Otherwise, this natural log cancels the exponent in the Gaussian, and we just get this negative quadratic. So we have to take the gradient of this. That's not too difficult. So there's different ways to do it, but one way would be to expand this into 4 terms. One term would be like xi transpose q inverse xi. Clearly, when you take the gradient with respect to mu k, that goes away. Then you have another term which is mu k transpose this. So when you take the gradient of that, you just get this. You might remember that from some homeworks. And then there's another term which is xi transpose this times this. If you transpose that, it's a scalar, you can just transpose it. Then you get exactly this term again. So that will basically turn the 1/2 into a 1. And then the very last one is you have this term. So this one, if you take the gradient with respect to mu k, you get 2 times this. And then that 2 cancels the 1/2. And finally, this is your gradient. And this is something we can evaluate. We can simplify it a little bit. Let's bring the q to the front, and we'll have this. Let's see. Yeah, once we do that, you can see that in order to set this whole thing to 0, we just need to set this vector to 0. We don't have to worry about what q inverse is. So we set this to 0, And if you just rearrange that, you can find that mu k has to be this. Okay, so this is our update of mu k, or optimized mu k. We'll set that at mu k t plus 1. And there's a similar process to optimize the covariance matrix Q, but just to save time, I won't give you all the details. And here's a summary of the algorithm. So you start with some initialization of your weights, your means, your covariances, and you just repeat this here. So you first compute these gamma k ITs. So if you think about this, for a fixed I, this is a PMF of the membership probabilities for the sample xi. So we compute this for all I. Next, we just do an average over I of that quantity to get these weights. So the weights are like an average over the samples version of this. And then we use these two guys here to get our means, and we use those and our means to get our covariance. Now that we have updates on these guys, we can compute better membership probabilities, and from the better membership probabilities, we can compute better parameters, and we just keep iterating. I'll show you an example, a pictorial example of this. Maybe it will make a little more sense. The last question is, okay, how do we initialize? So a very popular technique is just to run k-means for the initialization. So k-means does not give you the gamma k's, but you can just look at the fraction of samples that k-means assigns to cluster k and set that fraction as gamma k0. And to get the means and the covariances for the kth cluster, you just look at the samples that k-means assign to cluster k, and you just compute a sample average and a sample covariance of those, and that will give you these initial mu's and q's. So that's essentially how it goes. Computationally, if you have a large feature dimension D, you have D squared parameters in here. That might be too many, too computational. So often people restrict this to be a diagonal matrix just to save on computation. Then there's only D parameters here that you have to compute instead of D squared. So that's a common trick. Okay, but let's look at what happens with a pictorial example here. So we have this data set, and we have an initialization. Let's say that we put one of our means here, the other means here, and this circle shows us just one level set on the covariance matrix. So this would mean that we have a covariance matrix that's a scaled identity because it's a circle. As it gets stretched out, it's no longer an identity, it's something else, but this is just a simple initialization of Q at some scaled identity. Okay, so again, the first step is to compute the membership probabilities. We essentially now, we have capital K equals 2. So that means we can describe things with colors, red and blue. So the more blue a point is, the higher the probability is that it is associated with this cluster. And the more red a point is, the higher the probability that's associated with this cluster. And for points that are right in the middle that are kind of brown colored, they have equal probability of being in those two clusters. Okay, so for every point in our training data set, we had to compute this vector of two probabilities. First, the probability that it corresponds to this. Second element in the vector is 1 minus that probability, which is the probability that corresponds to this. And then we can just color each point according to that probability as a way of visually presenting the data. Okay, so this is the first step. The next step is we're going to fit those parameters based on those colored points. So we essentially want to now do a sample mean over all the red points. Well, actually, a sample mean over all those points but we're weighting them. They count more, the more red they are, the more they count in the sample mean. That's what this is saying here. And so as you can see, the sample mean weighted by the red points ends up being over here, and the sample mean weighted by blueness ends up being over here. Similarly, we compute the sample covariance with the same weighting, and we can see that the sample covariance, it gets stretched for the red, and this is the sample covariance for the blue class. So this is just after the first iteration, not really looking very nice, but let's say we do this. Now that we know these new means and covariances and everything, we can reevaluate our points and say, okay, this point over here, how much should that correspond to this Gaussian versus how much should that correspond to this Gaussian? And so we recolor all our points. And based on the recolored points, we can then compute fit new Gaussians. And we keep doing this. This is after 1 iteration, after 2 iterations, after 5 iterations, and after 20 iterations. And you can see things are gradually sorting themselves out until finally, this is what we get after 20 iterations. So it looks like we've done a pretty good clustering. There's the mean here. The covariance matrix is stretched a little bit to account for the shape of this data set. Similarly, the covariance matrix over here is stretched a little bit to account for the shape of that cluster. Okay, so works pretty well in the end. Is that making sense in terms of how the algorithm's working? Okay, so it is an iterative algorithm. It actually is reminiscent of k-means, but there are some differences. EM is always computing these soft assignments. K-means is always computing hard assignments. We call them k-hat. EM is estimating these covariance matrices, while k-means is implicitly using scaled identity covariance matrices with really small variances. As a result, the decision boundaries for EM are curved, where the decision boundaries for k-means are straight. Remember we had those Voronoi cells? They're piecewise linear, but once you have these covariance matrices and you take those into account, then things become curved, or at least maybe piecewise curved. EM is estimating these weights gamma, while k-means is implicitly using just uniform weights. EM is more computationally expensive than k-means, but it's trying to give you a better approximation. Both of them can get stuck in locomina. Both benefit from a good initialization, and both are implemented in sklearn in a very easy way. So here you can see like covariance type equals diag. This is telling us just use diagonal covariances. Don't try to fit the entire covariance matrix. And this is saying how do you initialize? Use k-means. Okay, so the very last slide then is let's do an application of this to a problem of color quantization. So this might seem like a strange problem, but the idea is it's a form of image compression where we want to use many fewer than the amount of colors that we usually allocate to an image. So this is most images. We represent a color image using 3 channels, red, green, blue. For each channel, we allow 8 bits or 256 different brightnesses, right? 256 brightnesses for red, for green, and for blue. So in total, there's going to be 8 times 3 or 24 bits per pixel. And if you think of all the possible combinations of red, green, and blue brightnesses you can get, there's basically like 17 million different colors that you can represent for each pixel. So it's pretty huge color space. What if we don't want to use 24 bits per pixel, but we just want to use 4 bits per pixel? That would be like 2 to the 4 is 16 colors. So instead of using 16 million or 17 million, I want to use 16. Okay, so what I have to do now is I have to figure out what are those 16 best colors. That's the objective. So you can sort of think about this. This is we're living in 3 dimensions here. So it's like we have red, green, blue. We have a data set which comes from all these pixels. So if you think about every one of the pixels, you can think of it as a vector in 3 dimensions. So you have, a whole bunch of data points in this 3D space. And what I want to do is I want to cluster in that 3D space. I want to say, yeah, there's one cluster over here, there's another cluster over here, and there's another cluster over here. And I want to get 16 of those guys. Right, I want to take this data set and cluster it into the 16 best clusters. And then the centers of those I will use as my new colors. And I'll represent my image using only those colors. And basically, because there's 16 of them, it's going to be 4 bits per pixel. Okay. So does that make sense, how we're setting this up as a clustering problem? Okay. So in particular, this image has 273,000 pixels. We're not going to use all 273,000 for our fitting because that would take too long. We're just going to take 1,000 random pixels throughout the image and do our fitting based on those 1,000 random pixels. And then once we figure out our clusters, we will quantize all the rest of the pixels down to those 4 bits or 16 points. Okay, so the last thing is just to show you the results. So this is the true image. The next one is GMM. The last one is k-means. Okay, so let's take a close look at the true image. So in the true image, you can see that there's a very nice gradient, like in the sky from blue to pink and so on. Similarly in the water, like things are changing very gradually. Once you quantize, you can see we no longer have all those different colors, right? So we have like, there's this color, there's this color, there's this color. So the sky basically gets like 4 colors total. The lake also, the lake gets just a few colors. But you can still make out the island pretty well. Let's see what happens with k-means. K-means, the island is definitely not as well represented. The sky looks similar, maybe, to GMM, but over here, this part doesn't look as nice. So, and this is sort of what you expect. K-means is similar to GMM, but a little bit worse. It's faster to run. It's not as, sophisticated because in Gaussian mixture modeling, we can essentially we don't have to use circular clusters or Voronoi cells with straight lines. We can get curved boundaries and so on. So GMM is a little bit more sophisticated. It works a little bit better, but it's a little more complicated. All right. Any questions on this last slide? All right. Well, that's it for the unit. And that is it for the course. So I hope you guys enjoyed it. I'd love to get your feedback on things like if there were topics you wish we had considered, let me know. I can take that into account for future semesters, or if there are things you liked or didn't like about the course, I can take that into account. I'll be teaching this twice next year, so I can take your feedback into account and try to make the course better. All right. Really appreciate all your hard work this term, and hope you learned a lot, and hope you enjoyed it. And so you still got a couple quizzes to submit, maybe Unit 11, this quiz, and then your final project. If you have any questions on the final project, please post something to the discussions. I'll try to answer it. All right. Hope your projects are going well. And yeah, if I don't see you, have a great summer.